Welcome! In this explainer, we're going to unravel a really powerful concept that, believe it or not, secretly organizes pretty much everything, from how you get ready in the morning to how massive software projects get built. It's kind of like a hidden set of rules that governs our world. So let's just dive right in. I mean, they seem totally different, right? But they all share one fundamental challenge. Some things absolutely have to happen before other things can. There's this hidden order, a set of rules you've just got to follow. I mean, this one's obvious, right? But this super simple idea of dependency, where one action must come before another, is literally everywhere. You just can't put on a coat before your shirt. That order is completely non-negotiable. And in school, we call these prerequisites. If you get them wrong, well, you just can't move forward. You have to have that foundational knowledge from one course to even start to make sense of the next one. Okay, so this isn't just a bunch of random problems. There's actually a specific and kind of elegant algorithm that's designed to solve this exact puzzle of order. So let's unlock it together. So this whole process of finding a valid order for a set of things that depend on each other, it has a formal name in computer science. And it comes with one really, really important rule that you absolutely cannot break. It's called a topological sort. And to put it simply, it's just a way of creating a to-do list for tasks where the order really matters. If task A has to happen before task B, this sort guarantees, every time, that A will show up before B on that list. It's really as simple as that. But, and this is a big but, this super powerful tool for organization has a critical limitation. It only works if one specific condition is met. And if that condition is broken, the whole system just grinds to a halt. The graph of your tasks has to be what's called a DAG, which stands for a directed acyclic graph. So what does that mean? Well, first, it's directed. The dependencies only flow in one direction, like from math to physics. And second, and this is the really crucial part, it has to be acyclic. That just means it can't have any loops. So why is being acyclic so important? Well, just imagine task A depends on task B. But task B also depends on task A. You see the problem? You're stuck in an infinite loop. It's a logical paradox where you can't start either task. A cycle makes finding a valid order completely impossible. Okay, so how do we actually do a topological sort? Let's take a look at the most common and probably the most intuitive way to solve this puzzle, an approach called Kahn's algorithm. The key to Kahn's algorithm is this really simple concept called indegree. All it is, for any given task, is a count of how many other tasks have to be finished before it can even start. It's just the number of prerequisites. The logic here is actually beautiful and simple. First, you count up the indegrees for every single task. Then, you find your starters, any task with an indegree of 0, and you pop them into a queue. These are the things you can do right now. Next, you start working through that queue. You take a task out, add it to your final sorted list, and then, here's the magic, you update its neighbors. For every task that depended on the one you just finished, you subtract 1 from its indegree. If any of those indegrees hit 0, bam, they're unlocked, and they get added to the queue. You just keep doing that. Pull from the queue, update neighbors, over and over until the queue is empty and everything is sorted. Now, you should know there is another way to do this using a technique called depth-first search, but Kahn's algorithm has a really crucial built-in feature that honestly makes it way more practical for most real-world situations. And here it is. This is the crucial point. It's this elegant little check. When you run Kahn's algorithm, if you get to the end and there are still some tasks left over that you could never process, that's it. It means they're stuck in a cycle. You don't need any extra fancy logic. The algorithm itself tells you directly if your dependency map is broken. This table really drives the point home. While both methods can work, Kahn's uses a queue, which is just a simple first in, first out line, and it has that critical cycle detection built right in. That's exactly why it's the industry standard for everything from software build systems to project management tools. So, now that you know the what's, the why, and the how, let's wrap this up with a few tips on how you can use this knowledge and avoid some of the common mistakes people make. So remember these key things. It has to be a directed graph. You always have to check for cycles, which, again, Kahn's makes super easy. Oh, and don't get thrown off if you find more than one valid answer. A lot of the time, there's more than one correct order to do things, as long as all those core dependencies are respected. So what's the big takeaway from all this? Topological sort is your go-to tool for bringing order to any system with dependencies, but it has that one non-negotiable rule: the system cannot have any cycles.
And when you need to actually do it, Kahn's algorithm is going to be your best friend.
Now that you have this way of thinking, you're going to start seeing dependencies everywhere, from building an AI pipeline to planning a complex project, or even just figuring out the steps to cook dinner. You now hold the key to untangling any complex set of tasks.